Hi class, we are now on 11.2b. This is colligative properties. Colligative properties are properties of a solution that do not depend on the type of particles that are dissolved, but rather on the number of dissolved particles in the solution. There are three common and important colligative properties: freezing point depression, boiling point elevation, and osmotic pressure. In this lesson, we're going to briefly examine each of these properties. So, freezing point depression. Let's begin with freezing point depression. The extent to which the freezing temperature is lowered depends on the total concentration of dissolved particles. The more dissolved particles, the lower the freezing temperature. In colder climates, salt trucks are common sight in winter. These trucks spread salt on roads to melt ice and snow. This works because a saltwater solution has a lower freezing point than that of pure water. Most salt trucks spread calcium chloride, as the chart shows. The freezing point drops more rapidly for calcium chloride than for sodium chloride or for sucrose. Why is that? So in this case, what this is trying to explain is that we don't live in an area where you need to salt the roads. Why do you want to salt the roads? Because you don't want ice on the roads. So what this does is it lowers the temperature when water can freeze. Why does it do that? It does this by blocking the water molecules from coming together. Think about people in a crowded room. The more people in a crowded room, the harder it is to you to get to your friend on the other side of the room. It takes longer and you have to bypass all these people. That's the same thing as salting a road. You're adding ions that the more ions there are, the more particles, the harder it is for the water molecules to come together. Thereby, you have to lower the temperature by removing more and more energy. Then it'll force them to come together because that's what they want to do at that temperature anyways. But you have to lower the temperature, which means it has to get to a lower temperature in order for it to freeze. And until it does, then it's not going to freeze on the road. So hopefully that makes sense about what we're discussing here. And that's what this is trying to show you. By adding these three substances, the water freezes at zero. But when you add these, you now see that it goes lower and lower. So you would want to use calcium chloride because it's going to have to get to -20 before the water is going to freeze on the road, for instance. So it actually doesn't matter, and we're looking more at how many particles than actually what it is. But in this case, we're starting out showing you what it actually is. So you can see with sucrose, it goes from 1 mole. Remember, this is not ionic, this is covalent. So that's why it's not going to do much. It's making a difference, but not as much. It's the same as we're going to show boiling point. You add antifreeze to stop your car from overheating. It's the same thing. Sodium chloride, you have 2 moles. Total ion concentration is 2 moles. But with calcium chloride, you have 3 moles. And that makes this the best thing that you want to use. So colligative properties depend on the number of particles, not the type. Sucrose is a non-electrolyte, and it doesn't dissociate into ions. If 1 mole of sucrose is dissolved in water, there is 1 mole of solute particles present. Sodium chloride and calcium chloride are both electrolytes. 1 mole of sodium chloride dissociates into 2 moles of dissolved particles, and 1 mole of calcium chloride dissolves into 3 moles of dissolved particles. Because calcium chloride dissolves into more particles, it drops the freezing point of water more than sucrose or sodium chloride at the same concentration. Because of this, calcium chloride is usually the salt of choice for melting ice on roadways. I'm sure some of you guys have lived where there's ice, so you will understand it better than me, who's been born and raised in Los Angeles. Boiling point elevation. The presence of dissolved solids also raises the boiling point temperature of a liquid. This property is commonly called boiling point elevation. Like freezing point depression, this property depends on the number, not the type, of solute particles present. One important example of both freezing point depression and boiling point elevation is the use of mixtures as engine coolant. Automobiles must have liquid coolant to carry excess heat away from the engine, but the use of pure water in a coolant line is risky because water freezes at 0 degrees Celsius and has a boiling point of 100. Because water expands when it freezes, water-filled lines burst in cold weather. In order to prevent this, ethylene glycol is mixed with water to form a mixture called antifreeze. A 40% by mass solution of ethylene glycol in water has a freezing point of negative 45 degrees Celsius. The ethylene glycol water mix also has a higher boiling temperature than pure water, about 106 degrees Celsius. This lowers the gas pressure inside the coolant lines and allows the engine to run hotter without coolant escaping as easily. So let's take a look at a problem. Which solution has the lower freezing point? A 3 molar solution of sodium carbonate or a 2 molar solution of aluminum chloride? To solve this problem, we must identify the total number of moles of ion present in the solution. So we're more interested in the number of ions than the actual solution. Sodium carbonate dissociates to form 2 sodium ions and 1 carbonate ion. A sodium carbonate solution with a concentration of 3 moles per liter therefore dissociates to produce 6 moles of sodium ions and 3 moles of carbonate ions per liter. This is a total ion concentration of 9 moles per liter. Similarly, aluminum chloride dissociates to form 1 aluminum ion and 3 chloride ions. An initial aluminum chloride concentration of 2 moles per liter results in an aluminum concentration of 2 moles per liter and a chloride concentration of 6 moles. The total ion concentration is 8 moles per liter. Because the sodium carbonate solution has a greater number of dissolved ions, the solution will have a lower freezing point. So let's take a look now. So we've now moved on to osmotic pressure. This is the last colligative property. Osmotic pressure is much different than the other two. This property is especially important for biology and health science applications. This property I'm repeating myself, because it profoundly affects the function of living cells. Cell membranes are composed of a thin double layer of molecules called a lipid bilayer. These membranes enclose the cell, holding the contents of the cell in place. The lipid bilayer is a semi-permeable membrane. This means that water cannot pass back and forth through the membrane, but most molecules and ions cannot. When the solutions on either side of the membrane have the same solute concentration, water flows equally through the membrane in both directions. However, if one side of the membrane has a higher solute concentration, the water will migrate toward the more concentrated side. This tendency of water to move toward the more concentrated solution is called osmotic pressure. So it's trying to dilute the more concentrated side. So we can show this in a laboratory by placing water in a saltwater solution on either side of a synthetic membrane. Over time, water will migrate toward the more concentrated side, causing the volume of the saltwater solution to increase. So it's trying to dilute the more concentrated side. Why does water do that? To understand this property, it is helpful to use an analogy. Imagine 2 towns with equal populations. Both towns are nice and people like to live close to work. People with jobs stay put, while those without jobs may move back and forth between towns. If the towns are on the same size, if the towns are the same size, and if there are the same number of jobs in each town, then the same number of people would move in each direction between towns A and B. But what if a new factory opened in town A? Suddenly, more people have a job in town A, and so fewer would migrate to town B, while people in town B are still moving to town A. The result is the population of town A increases, and the population of B decreases. Just as jobs keep people in town, the solute ions from a strong interactions with water molecules, Solute ions form strong interactions with water molecules, preventing them from moving across the membranes. The more concentrated a solution is, the fewer jobless water molecules migrate across the membrane. As a result, if 2 solutions are divided by a membrane, there will always be a net migration of water toward the solution with more ions, that is, toward the higher concentration. In this image, the white circles on the left show the water molecules that are bound to the ions. Because there are fewer free water molecules on the left, the net migration of water will be from right to left until the number of free water molecules balance on each side. Human and animal cells are very sensitive to solute concentrations and osmotic pressure. For example, if cells are placed in a solution having a low solute concentration called hypotonic solution, or one with low osmotic pressure, the water migrates into the cell, causing them to swell and possibly burst. This is hypotonic. On the other hand, if cells are placed in a solution having a high solute concentration, called a hypertonic solution, or one with high osmotic pressure, the water flows out of the cells, causing them to shrivel like raisins. Ideally, the solution outside the cell is isotonic, meaning that the concentration is the same concentration as inside the cell. So you want to avoid hypertonic and hypotonic. You want isotonic, which has the same concentration inside as well as outside. One very important application of this principle is the administration of IV fluids. They are very commonly used in hospitals to keep patients hydrated or to administer medicine. However, use of pure water in an intravenous drip can be fatal because the resulting hypertonic bloodstream can cause the red blood cells to swell and burst. So let's do a problem now. A 1 molar aqueous sodium chloride solution and a 1 molar aqueous calcium chloride solution are separated by a semi-permeable membrane. Which solution has a higher osmotic pressure? Will the water flow towards sodium chloride or calcium chloride? So basically, we need to look at this. Our colligative properties are what we're looking at. So the key to solving this is to identify the total concentration of dissolved ions. The water flows towards the side that has the higher total ion concentration because it's trying to dilute it. On left, we have 1 molar of sodium chloride. This means that the solution has 1 molar of sodium ion concentration and also 1 molar calcium chloride ion concentration. So the total ion concentration is 2 molar. On the right, we have 1 molar of calcium chloride ion concentration, but we have 2 molars of chloride ion concentration. This means that the total ion concentration is 3. So because calcium chloride solution has a higher total ion concentration, it has a higher osmotic pressure, the water will flow towards calcium chloride. All right, so again, colligative properties do not depend on the types of particles, only the number of particles dissolved. So we looked at freezing point depression, boiling point elevation, and osmotic pressure. So which of these, first of all, is not an electrolyte? So I'm just going to jump ahead, and you can see that C is not. That's covalent, shares electrons. Which solution has the lowest melting point? So since we're looking at colligative properties, we want to look at the one that has the most particles to it. That's going to affect the melting point, and that's going to be D. And as you can see, I put the numbers here. I meant to put them on the answer page, but I put them here so you can see why D is the answer. Which solution has highest osmotic pressure? So again, it's the one that has the most ions that dissociate, so it would be D, and you can see it has 8 compared to everything else. A 3 molar aqueous sodium bromide solution and a 1 molar sodium sulfate solution are separated by a semi-permeable membrane. Will the water flow towards sodium bromide or sodium sulfate? So it's going to dissolve. It's going to go towards sodium bromide. I did not break this one down for you because it's similar to the other example, and you can look at that one and then put this, work this one out. But again, if you have problems, we can do this together. Which aqueous solution has the highest boiling point? So again, you want the one that has the most particles. It's going to be A. Which of these solutions has the lowest freezing point? Same properties. You want the one that has the most particles to it. I also stopped breaking these down because now this will get you a chance to figure out how to break these down and figure which one has the most particles. And the answer is